Hello, Iman. Hello, Thomas. If you have any questions, feel free to unmute yourself. Okay.
Absolutely, will do.
Thank you. Yeah, let's start our third. Hello, everyone. Welcome to our lecture today. As a quick revision, we discussed in our last lecture the controlled multiple access techniques. And we need to have medium access control to enable as much as we can users to share the network resources. And also we want the receiver to be able to differentiate or distinguish between the different received signals. Okay, so we discussed the frequency division multiple access, and as Daniel liked to say, frequency division multiple access is frequency division. We divide frequencies between users. So at each frequency, the received signal will be h of I, x of I, plus z of I, where I is index for user. So the received signal for user one will be the transmitted signal from user one attenuated by some channel losses plus the noise after processing the received signal. This will be the received signal at each frequency. In time division multiple access, we divide time. So each user will be allocated certain time slot to transmit with the full bandwidth. So at each time slot, the received signal at the base station or at the receiver will be the same equation. Okay, so using TDMA or FDMA, the base station is able to differentiate or distinguish between different received signals by looking. Oh, we are using now FDMA. So at each frequency, I expect to receive certain received signal from certain user. I am using TDMA, so at each time slot, the base station expect to receive certain received signal from certain user. But this has problem in terms of the number of connected users to the network. We have limitations on the number of users that can share the resources of the network, as we will divide the frequency. Till what? We can divide the time to time slots. Till what? So we have limitations. So we are going to use new technique that maximize the number of connected users in the network. This technique is called CDMA, code division multiple access. In this technique, in code division multiple access, all the users can transmit at the same time using the full bandwidth. But how can we will differentiate between them at the receiver? How? Yeah, using orthogonal codes. And we define what is the meaning of orthogonal codes. Yeah, perpendicular to each other. Or when we make dot product, the result will be zero. Okay, so we discussed an example or a game in our last lecture. As here, the received signal at if we have here the base station and we have two users communicating with the base station. User one want to send X1 to the base station and user two want to send X2 to the base station. At first, the user one will multiply its signal with code S1 and user 2 will multiply its signal with code S2. So the received signal at the base station will be the transmitted signal from user 1 attenuated by certain channel coefficient that represents the losses in the channel, plus the received signal from user 2, which is S2.x2, attenuated by some channel coefficient plus noise. So now, at the same time, the base station will receive multiple signals from multiple users at the same time. And our goal is to help the base station to differentiate or to distinguish between different received signals. How can the base station do this? We discussed a toy in our previous lecture, and we will repeat it again now. So, codes like languages. Okay, I speak Arabic and English. Daniel speaks French and English, for example. So we will repeat our toy again, our example again. I will speak in Arabic, okay, and Daniel will speak in English, okay. And let's see. Can you are the receivers? Can you distinguish or understand the message of Daniel at the same time when I am speaking in Arabic? Let's see. So, what should we say?
It's cold out today.
It is what?
It's very cold out today.
Very cold today. Okay. Okay. But try to make our power to be at the same level. Okay. Okay. So 1 2 3 الجو بارد جدا في كيلونا. Can you understand his signal?
Yeah.
Can you understand my signal? No. No. Okay. This is what happened in CDMA. Okay. So at first, the base station want to extract the Daniel signal. So it will adjust itself to understand only English. Okay. So at first, the base station will multiply the received signal with half S1. Okay, let's do it. We have S1 multiplied by S1 transpose. So if we take S1 equal to 1, 1, and if we take S2 equal 1 minus 1, we want to multiply. Yeah, let's go. S1 multiplied by half S1 transpose S1. So we have 1, 1 multiplied by 1, 1. So the result will be 2. 2 multiplied by half, so equal 1. So the result here will equal to here H1 X1 plus we will multiply half S1 transpose by S2. The result is 0 because they are orthogonal. Okay, so we have 0 and we have half S1 transpose multiplied by the noise. So here the base station was able to understand only the signal X1, the language of X1 only. Okay, using by adjust the base station to understand only the language S1, the base station was able to understand the signal X1. Okay, we repeat this process. Okay.
What if your orthogonal vectors don't have a length of 1? You're using half, and that obviously makes it like 2 divided by half.
Yeah, I know. So if here we have any factor.
Oh, it doesn't need to be half. It's just
Not, yeah. This is for simplification for you. But we can, if we want to amplify the received signal, we can adjust the received signal using this factor. Okay, so if you want to amplify the signal, okay, so you can adjust this stuff. We can also need to attenuate a little bit the signal. Okay, so based on this number, okay, we can adjust the signal. This is like adjust the volume up or down. Okay, the most important thing is to be able to separate x1 only in this equation. If we want to understand the signal is x2, we will adjust the base station to understand the language S2 only. So we multiply the same received signal by code S2 transpose. Okay, and do the same process. S2 multiplied by S1 will equal 0. S2 multiplied by S2 transpose by half, we will be able to extract X2 only plus half S2 Z. So this is what happened using CDMA. Adjust the language, I can extract one signal. Adjust the base station to the second language, I can understand the second signal. And go so on. Okay, this is the basic idea of CDMA. Is this clear to you? Okay, let's go through the topic of our lecture today. We will continue in the analysis of CDMA. Actually, we still have problems in CDMA. Okay, what are the problems? We have finite number of orthogonal spreading codes. The number of orthogonal codes are finite. So if I have 1,000 users, so I need to have 1,000 orthogonal codes. Okay, if I have 10,000, the number of orthogonal codes that I can obtain is finite. Okay, so I can't serve each user with unique code, which is orthogonal to all other codes. This is very difficult. Okay, this is the first problem. Also, we need synchronization. And I told you in our last lecture, the problem of CDMA is that we need synchronization in time. Here we need synchronization in codes. So the code that each user uses in the transmission must be known at the receiver. Okay, so this is very difficult process as we need synchronization between the transmitter and the receiver. Okay, this first, and this consume time, this consume processing. Okay, that's why the synchronization between transmitter and the receiver is very complex process. And this is in general, not only in communication network. Schemes built on or based on synchronization can achieve better than schemes that don't require synchronization, but they are more complex. Okay, so as you are engineer, you must make the trade-off relation. Okay, so these are the drawbacks or the limitations of CDMA. How can we overcome these limitations? Actually, we can use, instead of using pure or full orthogonal codes, we can use quasi-orthogonal codes or semi-orthogonal codes. What is the meaning of semi-orthogonal codes? As you know, when I multiply S1 by S2, the result is 0 if they are completely orthogonal. If they are semi-orthogonal or quasi-orthogonal, this result will not equal 0, but will be very small. Okay, so in this case, the received signal will be, we have H1, X1, X1 plus H2, S2, X2 plus Z. If I multiply here with half S1 transpose Y, this will equal H1, X1 plus H2, X2 with a factor which is very small. So in our previous case, it will this value equal to 0. Okay. Here, using semi-quasi orthogonal codes, the result will still have a result, but this result is 0, not 0. It's very small. Okay, plus noise divided by. Okay, so as you can see here, this can be acceptable solution, and in this case, the quality of the received signal will decrease. Because what? Because the received signal will suffer from noise and interference from the neighbors, our neighbors in the network. Okay.
How like small is it compared to the noise? Like when you almost just bump it up to one term and call it.
Yeah, you want to compare this term with this term?
Yeah.
Yeah, actually, at the end, this term and this term, we will sum both in order to calculate the total interference and the noise. Okay, so we are not interested to compare between these terms. We are interested to minimize the sum of this term. So, because of to understand this question, how can we measure the signal quality? How can I say this signal is a good signal and this signal is bad signal? For sure, you know. Okay. Yeah, that I want to discuss with Duncan, Daniel, Brenda. How can we say this signal is good or not?
Ratio of the noise to the signal.
Correct. So we can measure metric called signal to interference and noise ratio. Okay, from this terminology, signal, which will equal signal power divided by interference power plus noise power. Okay, for sure, we want the signal power to be greater than the interference power and noise power. In our previous case, when we have orthogonal codes, the interference term will equal 0. So this parameter can be calculated by dividing signal power to noise power only. But now, or in practical, we can't have orthogonal codes that can serve large number of users. So we will use semi-orthogonal codes. So we will have interference term. Okay, so we want to maximize the signal power, the signal received power to be accurate. Okay, and we want to minimize the sum of interference power and noise power. Okay, actually, I don't have control over the noise power because noise power are the noise. We obtain noise power from the processing of the signal using electronic devices. These electronic devices will have some noise by default. Okay, so I don't have control as communication engineer over the noise power. But if I am responsible for manufacturing this device, I will have control of the noise by enhancing the quality of my outputs, enhancing the quality of my design. Okay, this can minimize the noise power. But as communication engineer, I have the antenna, the product of the antenna. Okay, I have already used the antenna. Okay, so I don't have now control over the noise power, but I can minimize the interference power. How can this be done? Let's see. Okay, so here, as I told you, we will use semi-quasi orthogonal codes. So the multiplication, the dot product of S1 and S2 will not equal 0, but it will be very small. So we will have interference term will be presented at each decoded signal. Okay, so we will have a problem. This will affect our receivable rate. as if you remember from our last lecture, the rate of each scheme depend on log base to 1 plus signal to noise ratio. Okay, so at first, when the interference power is small, is zero, for sure the signal to interference and noise ratio will be large. So I can achieve larger data rate. But now we have interference term, so the value of the signal to interference noise ratio will be small, a little small. So this will reduce the achievable rate. And as you can see, our achievable rate depends on our power, our received power. Okay, and for sure, the received power depends on the transmitted power. Okay, so the received power depends on the transmitted power. Okay, and this will affect the signal to interference noise ratio, and this will affect the achievable rate. This clear to you till now? Clear? Okay. So let's discuss one of the problems. Okay.
The only thing I'm a little confused about, like, wouldn't that equation not take into account any sort of lost power on transmission? Because since we aren't actually directly comparing it with the transmitted power, like, sure, the received power.
Okay, so here we are dealing with the received power. What is the received power? The received power of the signal will be the channel loss square multiplied by the transmitted power. So I transmit, for example, with 1 watt. Okay, but because of the loss of the channel, the received signal arrived to you is 0.5 watt. So the losses in the channel can be represented by this factor that cause my transmitted power to be reduced from 1 to 0.5 watt. Okay, so we have losses in the channel. Also, as we know, power is inversely proportional with distance, square of distance. And in some model, it is proportional with distance power 4. Okay, so the signal attenuates by default. This fact, our signals attenuates by propagation in the free space. Okay, so we have a problem. What is this problem? This problem is called near-far problem. What is the meaning of near-far problem? This is the case that this is the base station, and this is the base station. Okay, and we have, I am here, and another user here. Okay. Okay. So this user is communicating with this base station, and the losses here, this user 1. User 1, and this is user 2. Here the channel is 1, 1. This base station 1. This base station 2. Okay, so here the channel is H2, 2. H2, 1, H1, 2. Okay, so we can form our channel matrix H11, H12, H21, H22. This matrix represents the channel attenuation between base station 1. This row is user 1. Yeah. Between user 1 and base station 1. And this between user 2 and this base station 2. Okay, okay. Here, as you can see, user 2 send message to base station 1. So the received signal at base station 1 will equal H11 S1 X1 plus H21 S2 X2 plus minus Z1. Okay, okay. What will we do? We will multiply, we want to decode the signal X2. We will multiply the received signal by S2 transpose Y1. Here we will obtain H21 X2 plus Z1 multiplied by S2 transpose, and here we have some factor. Okay, here S2 multiplied by S1 is not equal 0. Well, equal small parameter. But as you can see here, this user is closer than this user to base station 1. So the received signal from user 1 will at base station 1 will be greater than the received signal of user 2 at base station 1. Okay, so what's your opinion? The interference parameter here will be small or large? What? Small?
Which one? Interference?
Yeah.
From user one signal? to user
Again, we are decoding the signal of user 2. Okay? Okay. At base station 1. The power received from user 1 and the power received of user 2. How can we compare it? What is your opinion? User 1 is closer to base station 1. So the received power from user 1 is larger than the received power from user 2.
Yeah.
Okay? Okay, we agree. So if the received power of user 1 is greater than the received power of user 2, and we want to decode the signal of user 2 in the presence of interference of user 1. Okay? Because of the multiplication of S1 and S2 not equal 0 now. It has a value. Okay? So we have interference. What is your opinion about the amount of this interference? Will be small, will be large, will be has no effect? What's your opinion?
I think it might be a problem because it could be as big as the received signal.
Yeah, as the received power of the interference here is large, the amount of interference power will be increased, and this will affect our signal to interference to noise ratio, and this will affect the achievable rate. This problem is called near-far problem in CDMA. Okay, so the user who is near to the base station will cause or will produce larger interference to the far user from the same base station. This is the meaning of near-far problem. Near, the near user to the base station will cause a large interference to the far user to the base station. Okay, and if the interference is increased, the ratio signal to noise and interference ratio will decrease, the signal quality will decrease, and the achievable rate will decrease. This is the problem here. This is clear to you. You understand now. You must understand the problem to understand the solution. Okay, so the problem is clear to you. Okay, how can we overcome this problem? Actually, Qualcomm which is one of the biggest mobile operators, and they have large research center in the mobile communication field, found solution for this problem. Okay, how can we overcome this problem? Okay, so as you can see here, Qualcomm found solution in 1989. Okay, and we start using CDMA in practical by the end of 1998 or by start of this century 2000, for example. So we are making research first, study all possible problems, and after that deploy the technique in industry. This is the cycle of each technology. Make research, at first invent or discover the new technology, and make analysis to this technology, and analyze the possible problems, and try to figure out solutions to these problems, and make several tests, and then apply. So this problem was solved in 1989, and CDMA was applied in mobile communications by the end of 1980 or by 2000 in this region. Okay, so this is a hint for you. Okay, how can Qualcomm solve this problem? At first, the base station will calculate the ratio between the received power and the transmitted power. So the received power, as we can for each user. So the received power for the signal of user 1, this is user 1, will equal H11 square multiplied by the transmitted power. Okay, this is the received power. What is the transmitted power? Is the bit transmitted of user 1. Okay, so this ratio will equal the square of the channel attenuation. Okay, the base station we will simplify this parameter by saying that it is equal to GII. Okay, the base station will invert the result of this ratio and transmit it to each user as feedback signal. Okay, hey Daniel, you must adjust your transmitted power by this parameter. Okay, hey Daniel, you must adjust your transmitted power by this parameter. Okay, using by enable each user to adjust its transmitted power, and this parameter depends on what?
The distance.
Distance, maybe. Yeah, as distance is one of the losses of the signals. Depend on the channel losses. Okay, as not only the distance will make attenuation to the signal. There are many parameters that can cause attenuation to the signal, but the distance is one of the most important parameters here. Okay, so based on the losses of your channel, I will let you know as the user. By default, the user don't know what is in the channel. Okay, and the user can't make analysis for the channel before transmission, as we are using mobile phone. Okay, transmit the signal, but the base station has the capability of making analysis of the channel and making analysis of the quality of the channel, and it can communicate through using feedback channels to the users. Hey user, your transmitted signal I received in the previous time slot was bad. Please adjust your transmitted power by using this factor, and this will enhance the quality of your transmitted signal. The users would say, okay, I will adjust my power and transmit again. Okay, this is the solution here. Let's repeat our example to make you understand this problem more. Again, we'll say the weather is very cold today, okay, but you will say it in very low power, and I will speak in very large power. Try to speak with low power as much as you can. Okay. Okay. 1 2 3. الجو قارس جدا اليوم. Did you understand his signal? Did you understand my signal? Why you can't speak Arabic? Okay, this is the problem of near far problem. Here, he transmitted a signal, but because of the large distance, the received power was very small. And because I am very closer to you, my transmitted power was very large. So I made an interference to his signal. So you as a receiver, you were unable to decode his signal or to separate his signal. This is the problem. But if you are the receiver, you will what should you tell me?
Power?
Yeah, you will tell me, hey Mahmoud, please low down your volume bar. Yeah. Hi Daniel, please increase your transmit power. Okay, so both Mahmoud and Daniel will receive your feedback, and we must respect your feedback. Okay, so I will adjust my volume power, and Daniel will adjust his volume power, and now we have feedback. Okay, so let's transmit our signal again. Okay, but when you multiply your factor here, this must increase your power level. Okay, as the channel losses in Daniel was very large when we invert. Okay, so this must maximize the power, and the same for me. I have little channel losses. When we invert, this will reduce my power level. So again, we adjust our power level. Again, 1 2 3. الجو قارس جدا. You can understand this. This is the technique used in the base station. Okay.
Coming back to like the beginning of the problem, why is base station 1 even picking up user Q signal when it's closer to base station 2? Like,
yeah,
controllers say that that's not your.
This is a very good question. Yeah, actually, as a user, you are not communicating with only one base station. If it is possible to communicate with more than one base station, you will communicate. This will enhance the received signal. As at the end, these base stations will cooperate together to serve you. Okay, so at one moment here, at the first time slot, the received signal at base station was very bad. But for sure, the quality of the received signal at base station 2 was better than that in base station 1. Yeah? Mm-hmm. Okay. So in this time slot, you are served through using base station 2. Okay. But after you adjust the power, you will be served using the two base stations. So for example, if I am the instructor of this course, okay, I am the instructor, your instructor. Yeah. Okay. And after this lecture, you will have the same lecture again with different instructor. Okay. So repeat the same information to you. Your knowledge will increase or decrease, or will be the same.
Probably increase.
Will probably increase or be the same, but not decrease. Yeah. So if you are served by using more than one base station, this will increase the quality of your received signal in the downlink. Okay. Or maybe have no effect, but for sure will not decrease the quality of the signal. So this is the basic idea. Okay. This is a good question.
And this is all just because like we have a limited number of orthogonal
Yes.
codes, right? So if we had like unlimited orthogonal codes, this would be finished.
Yes. Okay, but as you can see here, we adjust the problem. We redefine the problem of near far problem to be in terms of we want to have users to transmit in equal power. But in fact, we don't need this. We don't want this. This was the first step to solve our problem. So the first idea, when I told you, we have a problem. What is the problem? One user transmit in more power than another user. And this user cause interference to all other users. How can we solve this problem? You will tell me that, okay, tell the user who transmit in high power, please to reduce the power to be as equal as all other users. Okay, this is good solution and it can solve the problem, but this is not the optimal solution. We still have another optimal solutions. Okay, as when I reduce the power of Mahmoud, for example, you reduce my quality and you reduce my changeable rate. Okay, so no, the problem achievable rate, our rate. Okay, so our problem, we can redefine our problem to be, we want each user to achieve certain quality of service, certain quality of signal. Okay, and how we can measure the quality of signal?
That's not.
Using SINR. So instead of telling users to transmit in equal powers, no, we will optimize our network to allow each user to achieve certain predefined signal to interference noise ratio. Okay, and this technique is called distributed power control. Okay, in distributed power control, we want each user to achieve certain SINR value. So Duncan will achieve SINR1, which will be different from my SINR, which will be different from the SINR of even, and so on. For sure, each user has its own signal to interference noise ratio. How can this done? So here, this is the equation of signal to interference noise ratio. We have the this is equivalent to. Okay, so this is the received power of user one divided by the total attenuation, the total interference from us, from all other users. Here in this example, we have only one user. What we have to, here in this example, we have two users, sorry. What if we have 4? So in this case, we have 3 users cause interference to user 1. What if we have 10? We have 9 users cause interference to the signal of user 1. So the summation of all interference terms plus the noise. Okay? Where B is the transmit power of user I, and sigma I square is the noise power, and this is the attenuation, the signal is the channel attenuation, and we want our achievable or our actual signal to interference ratio to be greater than or equal certain predefined threshold value. Okay, so how can at each time, now we at time t equal 1, we know the transmitted power. This is the initial value of each user. Okay, after that, the base station will tell the user to adjust his power level. How? It will divide the required SINR value with the actual SINR value at time t and multiply it by the transmitted power at time t. Again, at first, all the users will transmit a power P transmit, the initial value. We don't know any problem about the channel. Okay. After that, in the second time slot, before the start of the second time slot, the base station will tell you to adjust your power by the ratio of the required signal to interference and noise ratio divided by the achievable signal to interference noise ratio at time slot t. Okay, so based on this ratio, okay, we will define the transmitted power at time slot t plus 1, and this will be your transmitted power. Okay, and we will iterate until we achieve the make this ratio to equal 1. Okay, so if this ratio equal 1 means that your achievable signal to interference ratio at time t is equal to the required signal to interference ratio. Okay, so the problem, our optimization problem, for sure we want to minimize the power, but at which level this will be the result of our optimization problem? We want to minimize the summation of all transmitted power subject to certain constraint. This constraint is that we want the signal to interference noise ratio, the achieved one, to be greater or equal the required one or threshold value. Okay, so we can represent this constraint using this equation. If we can calculate the threshold value will equal this parameter divided by this parameter, and we can obtain this. Is this clear to you, or this clear to you all? Okay, so actually this problem is very simple. It is linear program. You can do it easily in MATLAB, and I already did it. And I will upload the MATLAB code to you, okay, to understand how we can solve this problem. So, for example, here, yeah, we have the channel gains, and we have gamma is the threshold value of each user. So for user 1, we want to have signal to noise ratio equal 4, and for user 2, we want to have signal to noise ratio equal 3, and we have the initial power for user 1 0.1, and for user 2 0.1, and we have the noise for each user 1 and 1. Okay, and we can calculate the initial signal to interference ratio. Okay, so after that, we want to have the signal to noise ratio for each user minus the threshold value to be very, very small as we can. We want it to equal 0. But in MATLAB, we give some tolerance, so we want it to be very, very small as much as we can. This approximately is 0. Yeah. So at first, we will update the power using the ratio of the threshold value divided by the actual value multiplied by the transmitted power. And we will, again, using the new power, we will calculate the new value of the signal interference ratio. Okay, and measure the error value between the difference of the threshold and the predefined value. And we have while loop here. We will iterate until convergence, until we achieve the required error value. As you can see, if I make run here, you can see this result. So it takes around, so 4 is the threshold value for user 1, 3 is the threshold value of user 2, and as you can see, it takes around 6 iterations for user 1 to meet the threshold value, and it takes around maybe 7 iterations for user 2 to meet the threshold value. So this value will be used. So user 1 must transmit at power 4.7 and user 2 must transmit at power 1.9. Okay, to achieve the required signal quality. Okay, is this clear to you? Anyone has any question? I will upload this MATLAB code to you to understand more the basic idea of the distributed power control. And this is the example that what I discussed in the MATLAB code. Okay. If you have any question, feel free to ask me at any time. My office hour will be tomorrow from 12 to 2. Okay. Have a good rest of the day. Enjoy, yeah. Okay, Iman and Thomas, do you have any question? Thomas? Okay, so I will end this. Okay, thank you all.